Dr. Loeb, if 3i Atlas were to change course or if it sent out smaller spacecraft or fragments of itself, how long would it take to arrive to Earth? Thank you for all that you do.
Thank you. So if it changed course and at roughly the same speed, not making it much faster, then it would take a couple of months or so, a few months, depending on exactly the details. And in fact, that was worked out in a paper that I co-authored in the middle of July that was published by now in a peer-reviewed journal, along with Adam Hibberd and Adam Kroll. We considered the possibility that 3i Atlas is a technological spacecraft and asked what kind of a velocity shift does it need to have in order to reach Earth at a particular date. And you can look at our plots and you will see for any target date, there is a different velocity shift that it needs to acquire at an earlier time. And so we give all kinds of scenarios for that.
3i Atlas is changing course in ways that are not accounted for by standard gravitational models. After its closest approach, its trajectory should have converged toward a stable, predictable outbound path governed almost entirely by solar gravity. Instead, successive orbital solutions show continued deviations that require persistent, non-gravitational forces. These deviations are not isolated anomalies or data artifacts. They appear consistently across independent observations and remain significant even as the observational baseline improves. Rather than shrinking with additional data, the uncertainty in future position increases. This behavior is unusual and establishes the central problem. Any physical explanation of 3i Atlas must explain why its motion continues to evolve after the dominant gravitational encounters are complete. Early interpretations of 3i Atlas relied heavily on brightness to estimate its size. At large heliocentric distances, its luminosity was higher than expected, leading to initial estimates of a very large nucleus. As closer and higher resolution observations became available, those estimates were revised downward substantially. Current constraints place the nucleus on the order of roughly 1 kilometer in diameter. Under conventional cometary physics, an object of this size has limited surface area available for sublimation and should exhibit modest activity, particularly after perihelion. Instead, 3i Atlas continued to produce large quantities of gas and dust, comparable to comets tens of kilometers across. The discrepancy between size and activity is not marginal. It is orders of magnitude larger than expected and requires explanation. Structural integrity compounds the issue. A nucleus of approximately 1 kilometer shedding mass at the observed rate should experience significant weakening. Progressive erosion, fragmentation, or total breakup would normally be expected. No such behavior was observed. Throughout the period of strongest activity, 3i Atlas remained intact and coherent. This implies either an internal strength well beyond that assumed for loosely bound icy bodies, or a configuration in which mass loss does not translate into destabilizing stress. Existing cometary models do not naturally produce this combination of small size, extreme mass loss, and mechanical stability. Orbital dynamics provide additional constraints. The deviations in the trajectory of 3i Atlas cannot be attributed to gravitational perturbations from planets alone. Instead, they are best explained by non-gravitational acceleration arising from asymmetric outgassing. While non-gravitational forces are common in comets, their effects are typically smooth and gradually varying. In the case of 3i Atlas, the inferred thrust changes in both magnitude and direction. As a result, orbital solutions fail to converge toward a single path. Predictive models evolve from precise trajectories into expanding regions of probability. This behavior implies that the outgassing is neither isotropic nor steady over time.
Lucy was 240 million miles away from 3i Atlas, which is circled in the center, when its high-resolution LORRI camera caught the comet. You can see the comet's coma, the fuzzy halo of gas and dust surrounding 3i Atlas, and its tail, a smudge extending to the right of the comet.
As the data accumulated, attention shifted from where 3i Atlas was going to what it was leaving behind. The dust was the first clue that something was off. Not because there was too much of it. Active objects shed dust all the time, but because of how strangely uniform it was. Instead of the usual messy spread of particle sizes, the grains clustered tightly around a single scale, roughly 10 microns across. That number kept resurfacing in every calculation. Smaller particles should have been swept away almost instantly by sunlight. Larger ones should have been too heavy to lift at all. Yet these grains occupied a narrow physical sweet spot, lingering near the nucleus and scattering sunlight with unusual efficiency. When researchers modeled the density of this dust cloud, the result was unsettling in its precision. The cloud's optical depth sat close to 1, a critical threshold in radiative physics. At that value, the dust is thick enough to block a direct view of whatever lies inside, yet thin enough to remain luminous rather than opaque. In effect, the nucleus vanished behind a glowing haze. Telescopes could see light, motion, structure, but not the solid body producing them. This was not a typical cometary shroud. In most comets, dust production fluctuates wildly, optical depths rise and fall, and the nucleus periodically reveals itself. In 3I Atlas, the dust seemed locked into a narrow and persistent state, masking the core just enough to make firm conclusions impossible. The geometry of the dust made the situation even more difficult to interpret. Alongside the diffuse cloud, observers detected a narrow structure extending toward the sun. At first glance, this looked like a familiar illusion, an antitail formed when viewing angles align just right. But the numbers refused to cooperate. Models treating the feature as a mere projection failed to reproduce what was seen. Instead, simulations that assumed a physical jet predicted the structure in advance, and subsequent observations matched those predictions. For a jet to remain pointed sunward, its particles must be heavy enough to resist solar radiation pressure. Once again, the physics pointed back to the same 10-micron grains. The dust was not only uniform, it was behaving exactly as if it had been selected for this role. Light curves added another layer to the picture. The brightness of 3I Atlas did not rise and fall smoothly, as expected from a rotating body with uneven reflectivity. Instead, it pulsed. The variations were rhythmic, quasi-periodic, and persistent. Tumbling could account for some of this behavior, especially if the object were elongated or irregular. But tumbling alone could not explain the timing of the observed trajectory shifts. The idea that the jets themselves were turning on and off fit the data more cleanly. Pulsed outgassing would produce bursts of light as fresh material erupted, followed by subtle but measurable changes in thrust. Brightness and motion, two seemingly separate data sets, suddenly appeared linked. The scale of what was being lost made this interpretation harder to dismiss. In the month following perihelion, estimates suggest the 3I Atlas shed on the order of 10 million kilograms of dust. For an object roughly 1 kilometer in size, that is a significant erosion rate. Maintained over long periods, it would quickly exhaust the surface. This raised an immediate problem of longevity. If the object had spent millions of years drifting between stars, its outer layers should have been stripped of volatiles long ago by cosmic radiation. Yet here it was, shedding material at a rate more consistent with a freshly activated body. Either this activity had only just begun, or something had preserved those volatiles against expectations. Chemistry provided partial answers while opening new questions. Observations showed that carbon dioxide dominated the outgassing, not water. CO2 sublimates at lower temperatures, which explains why 3I Atlas was active far from the sun, in regions where most water-driven comets remain dormant. That detail fit neatly until it didn't. Over interstellar timescales, near-surface CO2 should have been depleted as well. Its presence in such abundance implies either deep reservoirs being accessed for the first time or a surface that had somehow avoided prolonged radiation damage. Both scenarios require conditions not commonly observed in small bodies. Then there was Jupiter. The giant planet's gravitational field is notorious for tearing fragile objects apart or flinging them into new orbits. 3I Atlas passed through intact. Its closest approach distance closely matched Jupiter's hill radius, the boundary where the planet's gravitational influence gives way to the sun's. After the encounter, the trajectory did not simply settle. Additional deviations appeared, consistent with continued non-gravitational forces acting during and after the passage. Instead of a smooth gravitational exit, the path showed signs of ongoing adjustment. As more pieces fell into place, the pattern became harder to ignore. The orbit of 3I Atlas was retrograde, yet aligned unusually close to the planetary plane. Its perihelion occurred during periods when observation was limited. The sunward jet remained tightly collimated across wide changes in distance from the Sun. Sustaining such a jet would require thermal and structural conditions difficult to reconcile with a small, rotating, icy nucleus. Even geometry seemed to conspire. The measured gravitational deflection near perihelion closely matched twice the opening angle of the sunward jet. There is no known physical requirement for such a relationship, yet there it was. Spectroscopy added further complications. Emission lines revealed unusual metal ratios, including elevated nickel relative to iron. Water, normally the dominant component of a cometary coma, played a secondary role. Optical measurements showed extreme negative polarization, a property not seen in ordinary comet dust. Near perihelion, the object brightened faster than any known comet and appeared bluer rather than redder, contradicting the usual trend as dust production increases. Radio telescopes listened and heard nothing. No artificial signals, no structured emissions. For some, this silence argues strongly for a natural origin. For others, it resolves nothing. The absence of transmission constrains only active broadcasting during the observation window. It does not explain the object's motion, its dust environment, or its chemical behavior. The difficulty is not that natural explanations are impossible. Many of the observed features of 3I Atlas can be explained individually by invoking rare compositions, extreme activity, or unusual thermal properties. The problem emerges when those explanations are combined. Each anomaly can be addressed, but rarely by the same model. As assumptions accumulate, the explanatory framework grows increasingly fragile. As 3I Atlas recedes and fades, the opportunity to collect new data narrows. What remains is a record of measurements that consistently point to an object operating at the edge of known behavior. Its size, activity, dust properties, chemistry, and trajectory do not align cleanly with established cometary patterns. Whether it represents an extreme natural outlier or something fundamentally different remains unresolved. What is clear is that its passage has exposed gaps in current understanding and underscored how much remains unknown about the diversity of objects that move between the stars.